Since last day we started optimization problems, right? Our main objective is to learn context optimization, especially the semi-definite programming cases, HDP cases. So last day we discussed about many different things. That is inside context optimization, what are the different classes that we learned? That is, first of all, we have LPP, right? Linear programming problem. After that, we have QP, quadratic programming problems. Then second order cone programming problem. After that is semi-definite programming problem, and the superset is the CP, cone programming, right? Lastly, we discussed LP, QP as well as HDP. I said that we will also learn a little bit the basics of SOCP and CP. Before that, this solving different type. Last day we solved two LMI problems, and specifically that those two belongs to FDP and also to the control theoretic problem. That is what was the first one? The Lyapunov inequality, right? When you say that is there exists a P equals to P transpose greater than 0 such that PA plus A transpose P negative definite, right? This is the inequality version of the Lyapunov stability theorem, and this is if and only, right? Actually, I should have written that at the beginning, that this is for linear time invariant system, right? So this is if and only if A is Hurwitz. That is, in other words, what we can say, the system is asymptotically stable, right? In short, I am writing A dot S dot. So this is for linear time invariant system, right? For which there is the Lyapunov stability condition, that is both necessary and sufficient. Like this, when we were learning the nonlinear, I said that Lyapunov is a sufficient stability condition. Please don't get confused between that. When it is for nonlinear system, that is in general, Lyapunov stability theorem is sufficient only. But when restricted to linear time invariant systems, LTI only, then it is not only sufficient, necessary as well, right? And that is the reason why you are using here if and only if. That means both necessary and sufficient. From that is what we learned, that is if you, right, so here P is the matrix variable, right, or we can say that is, of course here P is the unknown, and through this, by solving an HDP problem, semi-definite programming problem, that is we can find out this P, right, and then after that, even before this, the question will come, that is what is the LMI, that is we discussed all those things. Like the semi-definite programming problems, they are when we express this as an like inequality constraints or equality constraint, right? So for any optimization problem, what generally we do, minimize or maximize an objective function subjected to the constraints. Now, depending upon the type of the cost function and the different type of constraints, that is, we define all those categories. Like, for simply, if you have a NDP problem, then how do you define? It is simply, suppose, minimize C transpose X such that, or no, subjected to, you can write, yes, suppose first of all X equals to B and then Gx lesser than equals to H. So this is the cost function and these are the constraints. Okay, this kind of constant, whether it is equality or inequality, they are all called affine constraints, affine or linear. Okay. Affine or linear constraints. Why this name comes? Because you know this linear means the equation type of y equals to mx, right? So this is linear, and affine y equals to mx plus c. So now you can see that this can be represented exactly in the same fashion, that is as a b equals to ax or ax minus b equals to 0. So that's why they are called all affine constraints. Now it can be equality, it can be inequality, but these are all like class of linear constraints. Okay, but to be like technically more specific, we should say these are affine. Okay, now this cost function, it is linear. It is in the sense C1, like C transpose X, right? So how do you write it? C1 X1 plus C2 X2 up to Cn Xn, isn't it? So here C is given, A, G, B, H, all of them are given. That is, then you have to minimize this cost function subjected to this constant. Finally, here what is the decision variable? X, right? So what is the structure of X? This X is nothing but X1, X2 up to Xn transpose. So if you solve this linear programming problem, then finally, that is here, the search is for a particular X, which is of course the minimized value of the cost function subjected to these constraints, right? This is fine. Now similarly, that is, if you think about that, what is QPP? Quadratic programming problem. Now for that, like simply the constraints will remain the same, affine constraints, but the cost function will now become quadratic. So it will be in the form of minimize or maximize about half x transpose qx plus c transpose x. Okay, so this part is of course quadratic, but in a quadratic problem also, that is, there can be a linear part. So that's why this is the generic representation. So again, this is subjected to, suppose, this kind of constraints, x equals to b and gh lesser than equals to h. These are that is overall format of the optimization problems. Okay, so NPP and QP, like they are like quite like popular, and that is everywhere you will find such kind of problems. Okay, so LPP and that is QPP, that is fine. And now that is also, that is we discussed, especially in the control theoretic framework, we often like try to formulate our problems in the SDP framework. We discussed that reason, and so what were the reasons for which SDP is quite popular to like control people? Like first of all, that is with the SDP, that is also a class of convex optimization problem, right? And then here, that is both this cost function and the other things, they can be shown or they can be formulated using the LMI framework, and then the solutions become easy, because for solving the SDP problems there are many semi-definite programming solvers, right? What are the SDP solvers? MATLAB LMI solver, then CBX, Selumi, Yalmi, Gurobi, Mosaic, all these solvers are available, especially the CBX, Yalmi, Selumi, all of them are quite user friendly as well, and they work with MATLAB, that is from within, if you download that package, it is a third-party toolbox. So simply that is you attach or you put it into the root directory of your MATLAB, and then from MATLAB command window you call those functions. It is as if you were adding an extra library. Okay, and then that is by using those solvers you can easily solve this kind of problem. Now that is when we talk about this elements, linear matrix inequality. So what is a linear matrix inequality? That is, if you represent a constraint, like here you have constraint that is in the form of fx greater than 0 or greater than equals to 0. Okay, if this is strictly greater than 0, then strict constraint. If it is greater than equals to non-strict constraint. Okay, now this fx, it has a particular structure. What kind of structure? f0 plus f1x plus f1x1 f2x1 up to fnxn, suppose greater than 0, where in fi equals to fi transpose, all greater than 0, or in bracket I am writing greater than equals to, that is it can be greater than equals to as well. Okay, so here you can see all of these matrices, they are real symmetric matrices and also of the same sign. Okay, because you know that is summation of positive definite or negative definite matrices will have the same. So here that is ultimately, that is here not always, that is I am removing these constraints, removing this one because this may not always hold. Of course for some particular problems it will hold, but this symmetry property, it has to be symmetric. Why? Because otherwise the definiteness would not be maintained. Okay, so if you can convert a constraint into this framework, so then ultimately how you can write this? f0 plus summation of I1 to n fi xi greater than equals to 0, greater than 0, or even it is greater than equals to 0. If you can transform a constraint into this framework, then it is called a linear matrix inequality. Why a linear matrix inequality, or the same thing affine matrix inequality? Because it is represented in the affine form, as if this is the constant part and this is something like one constant matrix into variable. Okay, so that's why it is known as linear matrix inequalities or an affine matrix inequality. Okay. In the first problem, that is we learned that this PA plus A transpose P, which is not apparently in this form, but it can be easily translated into this form, right? That's what we learned. But that is very important for all of us, those who missed. That's why I'm referring, recapitulating what I taught the last day. Now suppose just for a 2 by 2 case, that is if you have a let P equals to P11, P12, we are considering symmetric matrix, so that's why here also it is P12, this is P22. These are all variables. Okay, so this is suppose P, this is unknown, so that we have to find, and A is known to us, it is A11, A12, A21, A22, that is known to us. Okay, now you simply expand what is given by PA plus A transpose P. So if you expand this term, then you will find that is we can easily represent this whole thing as some matrix into P11 plus another matrix into P12 plus another matrix into P22, and then it will be lesser than 0. Yes. So here I should have. You please like do this expansion because otherwise it won't be clear. So I believe the first one it would be 2A11, right? 2A11. This is probably A12. This is also A12. This is 0, right? The third one it must be 0 and
A21.
Yeah. This is A21. Here also this is A21. Here it would be 2A22. These two are like right. Of course, this is symmetric and easy to remember as well. In between, this one will have some more entries, right? What was the term? So this one?
2A21.
2
A21.
A21.
A22 plus A11.
A22 plus A11. Here also you will have A22 plus A11, and here
2A12.
Isn't it? Now you see, it is like as if f1 into x1 plus f2 into x2 plus f3 into x3 less than 0, isn't it? So as a whole, this you can designate by f1 x1 plus f2 x2 plus f3 x3 less than 0. That is fx less than 0, where that is f as a whole, that is if I equals to fi transpose, right? And here you don't have f0, because if you had any other terms here, say for example pa plus a transpose p less than minus 2i, then that constant matrix would have been f0, but at this moment here f0 is 0. Now, I also mentioned that is when we are talking about this kind of optimization problem, although the name is optimization, but within which we always have two type of problem, right? This SDP, then one is the just feasibility checking problem, another one is the minimization problem, right? So, one is the feasibility problem, another one is the optimization, like minimization or maximization, whatever maybe. So then mainly two class of SDP problems. One is the feasibility, like in this case, suppose a linear time invariant plant is given, okay, a matrix is given, whether you can find a positive, real positive, symmetric positive definite matrix P such that PA plus A transpose P less than 0. So this kind of problem is called feasibility problem. Okay. Now, if you compare with the LQR problem, where you have a cost function and then the control input you can find finally by minimizing that J function. That kind of problem is called minimization problem. Okay. So if I write it, it is more or less in this category. So the LQ1, what is your J function? That is what is the PI or the cost function. If it is infinite horizon LQR problem, then 0 to infinity, it is half X transpose Qx plus E transpose R. That is your J function, okay? I mean the cost function. You see this is exactly in the quadratic format, right? And what would be your constant? Of course, the first constant would be the x dot equals to ax plus bu, like the whole system constant. That's a differential equation constant, right? That too, that is we discussed. That is, if you don't place that constraint, then what will happen? This x and u, they will be completely independent of each other. But when we are doing it for whom? For a dynamical system, for which x and u, they are not at all uncorrelated. They are completely related by a set of differential equations, right? X dot equals to ax plus bu. That's why if you remember the LQR problem, then we say that is let x dot equals to ax plus bu be an LTI system with a, b being completely controllable. Then that is LQR problem means find out an optimal u function, u star of t, so that this j function is minimized where x and u are related by the dynamic equation x dot equals to x plus bu, right? That is your LQR problem. So this x and u, they are related by the system constraint x dot equals to x plus bu. Still, it is an unconstrained optimization problem. Why? Because so far we have not placed or we have not imposed any constraints on the magnitude of x or u. So that's why it is an unconstrained LQR problem. Now you can think about constrained LQR problem as well, because when we apply something for a practical problem, then of course there will be magnitude constraints on the state as well as control input. So along with the differential equation constraint, we place the magnitude constraint on the state as well as on the u. Say for example, if I say that is u in the scalar case, of course, just an example, that is u should always be within u min to u max. This is called a magnitude constraint on the control input, or rather simply a box constraint. Okay. Similarly, for state also you can impose such constraints. So if you have the state and input constraints, then we call it a constraint optimization problem, or in this case it is a constraint LQR problem. Okay. So in that way we have different type of framework. Okay. But J again it is expressed in a perfect quadratic format. So and if your Q and R, they are symmetric, positive, definite, then of course it would be a convex optimization problem. Once again, that is in the quadratic, that is when you express this in this fashion. Suppose your Q or R, or when you write in this fashion, suppose x transpose qx, if this Q doesn't have any definiteness, then we cannot say this problem is convex. Okay, it has to be symmetric, and then it must have some definiteness, at least semi-definiteness. That means it should be either positive semi-definite or negative semi-definite. But instead, suppose if it is a complex matrix, or if real but it is suppose an indefinite matrix, then the problem is not convex. Okay.
If it is not convex, then you cannot approach to eliminate it.
Like last day what we were discussing, if it is non-convex, then first of all, that is by applying some intermediate procedure, can we convert to an SDP problem? Like suppose you are dealing with a matrix, it is not positive, definite or semi-definite, then is it possible to work with its Hermitian part? That means suppose Q is not positive, you cannot say that is Q. So you cannot say that is Q greater than or equals to 0. Then can we somehow work with Q plus Q transpose, which is positive semi-definite? Q plus Q transpose means that we are working with the real Hermitian part, right? So in that way, somehow, that is by applying an alternative technique, if we can convert that problem into SDP framework. Okay, so that is one possibility, or else you have to apply the other type of nonlinear optimization problem, which is of course like it will be iterative and this is not at all straightforward. The main advantage of using the convex optimization framework is that here, if once you are able to formulate a problem in the convex framework, especially in SDP, after that you have the LMI techniques for solving that problem. Secondly, you don't have to take the headache of numerical calculation. Directly the software will give you the solution. And on top of that, whenever you get a feasible solution, that means if there is a local one feasible solution means of course there is a local minima, that will also be a global minima. Okay, so that is the main advantage of convex optimization. That is, once you find the solution, that is not only a local minima, it will also be a global minima, and that is mainly because of the convex set. Okay, so although we haven't yet discussed the convex set of the convex function, we will do it. But first, I wanted to just get you familiarized with the LMI techniques and how different type of control theoretic problems we can solve by using LMI. That's why after a little bit of introduction of convex optimization, I directly entered into the LMI domain. Okay, but we will come back to the core concept once more. So now, is this clear to you? So initially, you see, those who are not there in the last class, if someone asks you that is this PA plus A transpose P negative definite, from which we can at least comment that it is linear. Why? Because this P is a matrix variable unknown, but A is completely known. So here at least, first of all, it doesn't have any power, that is like square, cube, those kind of things are not there, and also there is no product of two unknown variables, right? So here you have that is P into A and A transpose P. In that sense, we can say that it is at least linear with respect to the P variable or the P matrix, right? But after that, why it is LMI or whether at all it is LMI, for if we have to show that, then you have to follow exactly the same fashion, okay? Because I said that is LMI means that kind of constraint can be expressed in this fashion, okay? And now that is we have said that is yes, PA plus A transpose P that can be expressed in this fashion, isn't it? So that is the meaning of LMI, and then that is like here you have understood that is okay, this is the matrix variable inside which you have three X variables, right, or the decision variables. In that way, and finally how it will be solved, that depends upon the which type of algorithm the solver uses. Like those who are attending optimization class, you must have heard about few type of like simplex algorithm, like simplex procedure, then interior point method. What other type of things you have learned?
Such techniques. Gradient descent.
Gradient descent.
Gradient descent.
Gradient descent for something else, but it's not an LMI finding procedure. But for finding the solution of LMI, there are this interior point method. Then some other techniques are there. Okay, so if you see any of the optimization rule, the void one is one of the best. Although that is quite a fat book, but still all these are discussed over there. But here the advantage of using the LMI framework is that here at this moment we are not concerned about how the solver will search for the solution. Here we are mostly concerned with how you are going to frame a control theoretic problem in the SDP framework, right? So that, as I said, this is one of the big advantage. That is, you don't have to think about that how this solution of E will come. Your job is to frame the problem in a convex optimization framework, or rather in an SDP framework, so that directly we can apply the LMI techniques, okay? And then the completely headache goes onto the solver. It is completely the responsibility of the solver to give you the solution or to check the feasibility. Okay, so that is one of the major advantage of using the semi-definite programming framework. So after this, we solved a very interesting problem like the state feedback. How can we design this K matrix, right? That was the second problem. So for that, we had to use the same inequality, PA plus A transpose P, but then we applied it onto the closed loop system, right? Instead of A, then we used A minus BK in that way, and then finally that is there. Initially we were stuck because right from the beginning we are getting that is product of two unknown variables. Then that is we applied the congruence transformation, and then we applied a change of variable and a substitution. Then finally that is we found the solution, right? So today again we will do that, but with just a bit more advanced case in the sense, last day what we did, then all the closed loop poles would have been placed exactly in the open left half. Now suppose if somebody asks that is okay, that is I want in a specific region, that too can be done, but at this moment by this specific region I want it to be, if somebody says that is okay, suppose this is a minus sigma line, that sigma value can be 1, 2, 5, 10, and then I want all my poles placed in this region. This is one kind of performance constraint. Why performance constraint? If you can maintain this one, then finally in the closed loop response, it is guaranteed that, let me clean the board a little bit. Can anybody tell me the interpretation of physical significance of placing the poles beyond a point?
Decide the frequency response.
No, not because here this is related to time response. It decides the damping or the exponential envelope. Whatever response you have, it will be covered within this envelope. That sigma is that sigma. Okay, so that can be incorporated through the LMI. That is really an useful technique. We call this a state feedback solution with a prescribed degree of stability. State feedback design with a prescribed degree of stability. So how would you formulate and solve that problem using the LMI? Please check last days how we wrote, and then you suggest in this case how would you write? Last day we solved the state feedback problem, but there was no additional constraint. Now today we are going to solve the same problem, but in the presence of a additional constraint, right? How can we write or how can we proceed?
So shift the eigenvalues of A minus bk by this sigma value.
Then that is how will you write?
A minus sigma bk.
Of course, A minus sigma bk. Then A minus last time that is we had that A minus sigma bk has to be Hurwitz, right?
Yeah.
Now, not only Hurwitz with some additional constant. So that's what I wanted to mean. How would you write in that case?
Usually, like A minus sigma bk is Hurwitz, and then B into A minus.
This constraint, like all the poles would lie in the left hand side of this minus sigma line. How can you write that constraint? That is, whatever pole we are going to get, that means eigenvalues of A minus bk, the real part of all those eigenvalues must be less than minus sigma In that way you have to write. So you can write it like this. Design a K belong to Rm cross n such that real part of design a K matrix such that this happens. If you compare with the last days, what did I write? Simply that is A minus BK is Hurwitz, right? Now here, not only A minus BK is Hurwitz, its real part, like if all the poles of eigenvalues are placed in this region, then what is the condition? That is the real part of all those design eigenvalues or the poles must be less than minus sigma, right? Accordingly, I have written this. Now, this is actually the problem statement. Next job is you have to convert this into a matrix inequality problem. Rather, we are just going to like design it or formulate it as an HDP problem, right? Now, HDP problem means the constraint would be some inequality format. Now, initially the inequality may not be linear. You have to make it linear if possible. If this is your design problem and if somebody asks you, that is you convert or you formulate this problem in an inequality framework, then which is the first inequality come into your mind? The Lyapunov inequality, because this is already the Lyapunov stability theorem. This is for open loop system, no question of feedback. Now we are going to do the same thing for the closed loop system, right? So for the open loop, if the system is originally Hurwitz, then of course we can expect a positive definite P matrix such that PA plus A transpose K negative definite, right? Now if the same thing this happens in case of a closed loop system, that means suppose A comma B is fully state controllable, then it is guaranteed that is a K matrix will exist so that A minus BK will be Hurwitz. If it is so, then that Hurwitzness of A minus BK, that is equivalent to the existence of a positive definite P matrix, so that P into A minus BK plus A minus BK transpose into P less than 0. In that way we are going to write. So then if and only if there exists a symmetric positive definite P matrix and a K matrix such that you write the Lyapunov inequality A minus BK. Now simply A would be replaced by A minus BK. That means we are now doing it for the closed loop system, right? So P A minus BK plus, in place of A transpose it will be A minus BK whole transpose into P. Earlier we had only less than 0, but it is now the constant is not only Hurwitz. We have some additional pole constraints. So here there is a particular condition by which we can achieve it, that is minus 2 sigma P. Okay, and here there exists a P, that is this. Now here you cannot solve for both P and sigma together, because in that case it would be product of two unknowns, right? So it has to be, that is there exists a P greater than 0, K and a given sigma. Okay.
So can we not write A minus BK plus sigma is Hurwitz?
A minus
BK plus sigma I is
हाँ
Hurwitz.
हाँ
You can solve it.
Yeah, ultimately it will translate into the same thing. You are right, Sudarshan. That is here the condition. What he has said, that is correct. That is earlier what we wrote, that is suppose after this, that is we can write that is A plus BK or A minus BK plus sigma I is Hurwitz. Exactly the same. Good. Then even a better language would be for a given sigma greater than 0, comma, there exists a P equals to P transpose greater than 0 and K equal to R M cross N such that now you expand the inequality. Okay. This is a better sentence because here sigma is given, that is not a variable, right? So that's why that is I have like changed its position. Now that is if I expand that one, it is going to be PA minus PK plus A transpose P minus K transpose B transpose P plus 2 sigma P less than 0. Is it fine? Now that is every line you should start with the prefix, okay? That is for a given sigma greater than 0, all this. Starting from the beginning up to such that simply this I am not writing here, but you should write everywhere, okay? I am now that is simplifying or simply working on the LMI only. Here you see the problem is, I hope you have already found that is what is the source of nonlinearity. Like see, P is a variable, fine. But PA is linear, we don't have any pressure regarding that. A transpose P, that is also linear. But the problem lies here, PVK. And that too, why it is a problem? Because not only the fact is that here you have the P is unknown, K is unknown, but also there is a known term in between. Why? Because suppose if you had, say for example, if these two unknown terms P and K would have appeared in this fashion, suppose they are sitting next to each other, then you could have clubbed them into a single variable Q, and then it could have been a new LMI variable, right? Last day exactly this thing I explained, but today we are revising that once more. Are you getting? That is, if the unknown terms, not only 2, it can be 3 as well, if they are sitting next to each other, then you can replace them just as a block. That is, suppose you have P and K, you are going to like to replace it or substitute it by a new variable. Then in place of that, but of course P is separately appearing. Okay, so that is in this case, suppose if this is really possible, that P and K together we are going to replace by Q. So at this moment we had the LMI variables P and K. If this substitution would have been possible, then it would be with respect to P and Q, not K. This is an important point. Please remember, when you substitute or when you group some unknown variables by a new one, then that is you must be careful, like all the variables which you are grouping, they should not appear separately. Once more, that is P and K. Here already you see P is appearing separately, right? If it happens, that is suppose P is appearing separate individually, K is also appearing individually, and on top of that you have some other terms where P and K are coming together, then you cannot substitute. Are you getting? That is a highly important point. Why? Like suppose P appears individually, K appears individually, then PK that also appears individually. Now someone by mistake considering this as u, and then suppose like by mistake I am going to solve that LMI with respect to p, k and q. Will that be possible? Why not possible? Because if p and k are independent LMI variables, they will keep on changing on their own. But they are not free. Actually, they are coupled because you have decided that p into q, p into k equals to q. That is a new variable. So when the LMI solver will try to adjust these three variables at a time, then it is an infeasible constraint. Do you agree with that? Once more, if p and k appears individually, and on top of that you have a coupled term pk which you want to substitute by a new variable, by mistake suppose you are proceeding with that, then what will be the problem for the LMI solver? It will try to find out, or it will try to adjust these three variables independently. But p and k, of course, they are independent, but now you have one more constraint where p and k are coupled. That is the problem. So before substituting two or three variables, you must be careful about that all the ingredients should not appear separately. One or two of them, like suppose if there are three, x, y, z, two of them can appear separately and then you group. But it should not happen that all of them are appearing separately. Then this kind of situation will happen. Is this fine? Now you see, even here we have one more problem, that these two unknowns, they are not sitting next to each other. If that would have been the situation, we could have immediately substituted that pk by a new variable, then we would have succeeded. But that is unfortunately is not happening in this case. Are you getting, all of you? That is here, it is a product, but unfortunately you have an own term in between, right? That is a problem. Now that is like, if you are beginner, of course that is you will tend to think, okay, what is a big deal in it? Then as a whole, this triplet pbk I can substitute by q, because k is not appearing independently, b is not also appearing independently, and on top of that b is a known matrix, that is not a variable. If that is your substitution, then what the form it will take, that is PA minus Q plus A transpose P minus Q transpose plus 2 sigma P less than 0. It is of course linear in Q and P for when sigma is given. But would you succeed with this? I have posed one problem, the substitution problem, that is that you have understood. Now suppose if you like substitute for this whole triplet PBK, then of course it is now an LMI in P and Q. Okay, well, will this serve your purpose or our purpose?
So if we take another equation, Q equals to minus Q transpose.
But that is here not possible, right? Because PBK not equals to K transpose B transpose P. Can anybody tell me that is in this case what problem you are going to face? Think about that here. What is your primary objective? To design a K matrix, right? Isn't it? Then whatever solution you are getting, finally you will have to retrieve that K matrix, right? Now if your substitution is PBK equals to Q, and now suppose you have got the solutions Q as well as P, then from that what is the next step? Your BK equals to P inverse Q. Up to this much it is fine, but from this step can you uniquely find K? That would be the problem, because B is a non-square matrix. That is the problem. So that's why although substitution is a convenient and easy method, but you have to be careful that where you can substitute, where you cannot. These are some of the problems with LMI which are not written in any of the books, which when you work on LMI, that is gradually it will come with experience. So that's why that is whatever problems I faced, I am sharing with you so that you can learn quickly. These are practical problems with LMIs. If now this is the situation, then what alternative we can do here? That is it any way possible to bring this P here?
Congruence.
But before that, that is why should we go for a congruence? That is somewhere it is the requirement is somehow to like shift this P here. If not exactly P, at least P inverse. Why? Because P inverse we can declare as a new variable Y. So for this case, for this term, we will look for if this P can be placed shifted here, and similarly for this term, whether this P can be shifted here, so that you can get the two unknowns sitting next to each other. For that, the only like the method that we have may not be only, but still the most convenient method is that you pre and post multiply this the whole expression by P inverse and P inverse transpose. That is called congruence transformation. I will write, don't worry. What I wanted to mean, that is I am going to pre and post multiply the whole thing by P inverse and P inverse transpose. Then what will happen? Then this P inverse into P, that is I, so it is going to be A P inverse minus B K P inverse plus P inverse A transpose minus P inverse K transpose B transpose plus 2 sigma P transpose, sorry, P inverse. Here, what is the meaning of this symbol? That is P inverse whole transpose, right? Which is nothing but P inverse, because P equals to P transpose positive definite. The inverse of a positive definite matrix is again positive definite, and originally it is symmetric, so the symmetric property will be preserved. So similar to P equals to P transpose, P inverse will also be equals to P inverse transpose. Okay. Now that is the remaining step you please complete. After that we are going to do two small things, that is denote. We are going to bring in new variables. First of all, this Y colon equals to P inverse greater than 0. So now instead of P we are going to introduce a new Lyapunov candidate, which is your Y, and then you will find that this K and Y means P inverse, they are sitting next to each other. So what we are going to substitute, and Q equals to K into Y. So finally, the LMI that you are going to get, that would be in the variables Y and Q. No longer it is with respect to P and K. Please denote the difference. Earlier, we started the inequality condition with K and P, but finally, you see, when you have translated everything into linear matrix inequality, it is no longer with respect to P and K, but with respect to Y and Q. You please complete the remaining two steps. Okay? what will you get? AY plus YA transpose minus DQ minus Q transpose V transpose plus 2 sigma Y less than 0, right? Now, that is as you said, it is here. This one I can simplify. It is, you said that it is equivalent to as if we are that is getting this A minus BK plus sigma I to be Hurwitz. How does that come? See, that is E A minus EBK plus A transpose P minus A transpose B transpose P plus 2 sigma P less than 0. Okay. Then you take sigma P with each of PA plus A transpose P. What I am writing, like this is PA plus sigma P minus PBK. Then A transpose P plus again sigma P minus A transpose B transpose P less than 0, right? From this, can't you write that is A plus sigma I minus BK plus A plus sigma I minus BK whole transpose P less than 0. So that is nothing but A plus sigma I minus BK is ours. Is it fine for all of you? As we found the inequality version of the Lyapunov equation, similarly can we find the equality version of algebraic Riccati equation? Must be possible. I said that is from this PA plus A transpose P equals to minus Q. That right now is what I wanted to make your algebraic Riccati equation PA plus A transpose P minus PB I inverse B transpose P plus Q equals to 0. That is your AQ or ARE, right? Can we convert into an inequality form? That means either lesser than equals to or greater than equals to, we don't know which one would be appropriate. What is the first difficulty here? You have a, this is linear, fine. This is also linear, fine. Here you have a inverse. This is the first obstacle. But although this is a known term, okay. And then here you have a product of two unknowns. Like P is a variable, P unknown. So here you have this P as well as you have this P. if you ask that is sir what you are trying to find out, in case of Lyapunov what you are searching for? P, that is the solution. Here also we are searching for P. So if you that is readily convert into with the inequality, suppose we still don't know whether this greater than equals to or lesser than equals to which one would be appropriate, that we don't know yet. But suppose if you readily convert into like that, then presently what is the situation? Is it a linear matrix inequality? It's not, right? Because here you have like the coupling of like two nonlinear terms. But only thing is that is it has a particular pattern. Like this one is a transpose of this one, and in between you have something which is invertible. This type of thing, that's why I am about to write the Schur complement lemma. That is the best technique to be applied into such cases. Why? I am writing separately. These P, Q and R, no resemblance with them. Okay, this I am writing separately as if this is a partition matrix. Okay, so if this partition matrix is positive definite, then by Schur complement lemma, what you can write? This is if and only if R equals to R transpose greater than 0. Here initially the assumption is that P equals to P transpose and R equals to R transpose. Okay, that is the assumption. R positive definite. Then what is the Schur complement of this matrix with respect to R? I said with respect to R. That means R inverse will come into the picture. So you have to start from the element which is diagonal to R, right? So P minus Q R inverse Q transpose greater than 0. Okay? And since it is positive definite, so the other equivalent condition must also exist. That is P equals to P transpose greater than 0. And now what is the Schur complement with respect to P?
R minus Q transpose P.
Exactly. R minus Q transpose P inverse Q greater than 0. This is the strict version of the Schur complement lemma. There is a non-strict version as well, which also we should know. one of them will exist. Okay. Now you see this is R equals to R transpose greater than equals to 0. So the ordinary inverse doesn't exist. If ordinary inverse doesn't exist, then you have to go for the pseudo inverse, or in general we call them as Murray-Penrose inverse. So that is the symbol G. So this G is the pseudo inverse or Murray-Penrose inverse of R. But here you have one extra condition, that is Q into I minus R into Rg equals to 0. Okay. Now this condition will imply, that is it will come back to here if R positive definite. Murray-Penrose inverse. G for generalized matrix inverse. That is, here we cannot write R inverse, right? Because it is a positive. That is pseudo inverse. That is also a special case, because for pseudo inverse means that is if it is a non-square matrix and if that has a full row rank or the column rank, then you can find out the pseudo inverse. But suppose for a square matrix, if it is not a full rank, then directly we cannot write the pseudo inverse. There actually comes generalized matrix inverse, which was by these mathematicians Moore and Penrose. After their name, it is called Murray-Penrose inverse. Now you can easily see that is, suppose R is positive definite. So Rg equals to R inverse, then R into R inverse I, so that condition vanishes and then it will come back here. We may not need up to this much, but this non-stick version often we need, because many control problems you will find where strict inequalities is very difficult to formulate. Say for example, when if you apply or if you work with positive real systems or negative imaginary systems, there the inequalities would be mostly non-strict. In bounded real lemma, the inequality is strict, but for positive real and negative imaginary, all the inequalities would be non-strict. So there, the strict version of the should complement lemma doesn't apply. There we definitely need non-strict version. Okay. So this is one of the very important tool that is we need whenever we work in LMI. And the second one is what is that? Congruence transformation. Let us learn that one as well. one thing here little relay. I hope this you have heard in linear algebra, Sylvester law of inertia. How would it happen?
As far as I can remember, it is in Stang's book, but she didn't teach us that.
It is there, I think that is at the end part of chapter 6 or chapter 5. Convex transformation is there, after that Sylvester law of inertia, because these two are connected. The same thing I am writing in a short form, okay? Determinant is not equals to 0 means its inverse exists, okay? What is the meaning? That is, suppose M is a Hermitian positive definite matrix, okay? Then if you multiply that, if you pre and post multiply that M by any non-singular matrix, then the definiteness would be preserved, okay? Not only this much, there is something more, that is, which is actually, which was Sylvester's finding. I am going to write it. Can anybody tell me, that is, what do you mean by the inertia of a matrix? It is generally represented by n minus, comma, n0, comma, n plus. What does that mean?
Something related to eigenvalue. So how does it states rotate and
Not rotate, actually there is number of negative 0 and positive eigenvalues would remain the same after this congruence. This is called the signature of the matrix or inertia signature of the matrix. Inertia means it is represented by n minus, n0 and n plus. N minus means number of negative eigenvalues of that matrix. N0 means number of 0 eigenvalues and n plus means number of positive eigenvalues. Here you can ask that is, sir, how are you so sure that is all the eigenvalues it would be only like positive, negative or 0? Because since it is a Hermitian matrix, so it is guaranteed all the eigenvalues would be real. Then only you can write this signature, otherwise it is invalid. Okay. Now this congruence transformation means that is after this multiplication, that means after this transformation, this new matrix A star MS, it will also have the same number of negative eigenvalues, 0 eigenvalues and positive eigenvalues. So that is actually the general statement, not only about this definiteness. Okay, once again, not here what did I write? If M is positive definite, A star, that is what do you, how do you read it? A star MS, that will also be positive definite. But it is not only about maintaining the definiteness, the signature will also be maintained. Okay, so that was the finding of the mathematics of this person Sylvester. So that's why it is called Sylvester's law of inertia, and that is directly related to this kind of transformation. So that's why whenever you will read congruence transformation, here and there you will find the Sylvester law of inertia. অরিত্র, এটা তো ছিল লিনিয়ার অ্যালজেব্রা। আরে ক্লাসে তো সবকিছু নাই হতে পারে, তোমাদের তো দেখা উচিত ছিল। I give you a small thumb task. You next day you tell me the core difference between congruence transformation and similarity transformation. That is an important question for all control students, especially for PhDs. You know well about similarity transformation. This is also another kind of transformation, and the structure is more or less same. Here it is with only that is transpose or complex conjugate transpose, and in similarity there it is S inverse MS. So what are the main difference between congruence transformation and similarity transformation, or are they same? Of course they are not the same, right? But what is the main difference? That you search, I will ask you next day. Now coming back to the ARE, suppose it is less than equals to 0 or greater than equals to 0. Can you directly apply the Schur complement lemma to get it in a linear form? Because at this moment the main problem for us that it is still a non-linear matrix inequality. We have to convert it to a linear matrix inequality. That is really easy, right? You just try to match with the framework, that is here which part is P, which part is Q, Q transpose and R. So of course here PB means your Q, and B transpose P means your Q transpose. R is already there. This whole part PM plus A transpose P plus Q, that is actually your P. So can't I write that this is if and only if if and only if, tell me what should I write? PA plus A transpose P plus Q. That is my first entry. And the second one is PB. And then the third one is B transpose P. And then the fourth one is simply R, right? That is, suppose I am considering the first one lesser than equals to 0. Here I am assuming that is Q equals to Q transpose greater than equals to 0 and R equals to R transpose greater than 0. So that is here, if you directly apply the non-strict version of the Schur complement lemma, can't you get back the original inequality? So in this way, wherever you have this kind of form, that is this part is a transpose of this part, and in between you have something which is invertible and remaining part is linear, immediately you must remember about the Schur complement lemma. This is a highly useful technique by converting this kind of nonlinear matrix inequality into a linear matrix inequality. Now you see everything is linear. Or the main nonlinearity that we have, the product of the P terms, now they are split. P is the unknown, remaining all are known because Q or R, the weight matrices, they are given, right? Now here we have a glitch. Not in the sense of LMI, but whether it would be greater than equals to or less than equals to. You might think that this is a trivial fact, but no, not trivial. One choice is lesser than equals to, another choice is greater than equals to, right? Now you tell me that is which one is appropriate. Huh? Why not the lesser than? From should complement lemma only it will come, but just try to put your argument in a complete way. What is the logic? This is a very important question, and also the situation is quite tricky. That is, which one of them is appropriate? Okay, what do you think? That is, which one is appropriate and which one is not? Second one is appropriate. So, Moinak also says second one is appropriate. Then why are you saying so? That is why you are thinking that this one may not be appropriate.
Because
diagonal element R should be strictly greater than 0. You have to consider.
According to should complement lemma, please remember whether it is a matrix or a block matrix, these two entries, all of you please look at the board, that is this definiteness, like suppose at this moment this is lesser than equals to or less than, then these pivotal entries, that means this one and this one, should have the same sign, at least one of them. Once again, that is according to the condition of positive definiteness of a partition matrix, whatever sign you have here, that these two elements should have the same signature. Because otherwise you see the should complement lemma will fail, right? Now you see this is here negative semi-definite, but this R it is positive definite. So directly this is like one of them is contradicting the other. That's why this is not appropriate. This is one problem, and next that is what about the definiteness of this one? That is also another important point. That is, can you tell me that whether this PA plus A transpose P plus Q, can you talk about its definiteness? That is also difficult. Why? Because suppose originally the system is Hurwitz, then PA plus A transpose P, this part would be negative definite. But Q, that is greater than equals to 0. After adding, that is, the symmetry will be maintained, but we are not sure about the definiteness, right? That is the difficulty. Now, that is, you said the second one is appropriate. There also we have to think about that whether it is truly appropriate or not. Let's see. So this is greater than equals to, your R is positive definite, so at least this fact readily conforms with the non-stick should complement lemma, fine. But the problem with the first term, that will again come here. So, but since there is here R is positive definite, so like finally even if that this doesn't have a definiteness, but it may work subjected to the choice of Q. Why? Because if you come back here, what is the condition? That is, as I hold this greater than equals to 0, if and only if R positive definite and then P minus Q R inverse Q transpose greater than equals to 0. Here, that is, the condition is only P equals to P transpose. We don't need a definiteness here. That's why. But now the same thing would have been difficult if you consider a strict negative. That means, suppose if you solve for negative definite, then it would be a problem. See, PA plus A transpose P plus Q, it can be negative definite, but not for all Q. For some Qs as a whole, it can be negative definite, right? So then, for negative definite case, it will solve for such kind of Q matrices, not all.
Then R will always be positive.
So that's why here I have mentioned. That is, for NQR problem, Q equals to Q transpose positive semi-definite, but R has to be positive definite always. Why? Because ultimately we need the R inverse. R has to be positive definite. Okay, it cannot be semi-definite. So that is about, like, in case of Lyapunov, we didn't face this problem, that is which one would be like, in case of Lyapunov, there is no chance that this could have been greater than equals to 0 or greater than 0. But in Riccati, really you have that possibility. And ultimately you see that is, if you directly match with Lyapunov, you will tend to write it as lesser than equals to, but which we found that is no, this is inappropriate. Rather, the greater than equals to 0 is the appropriate. Let us take a small break, and after that I will solve only the one more LMI, and then we will finish. same problem. There initially we were not able to club those two matrix unknowns into because they were sitting like in between. There were known matrix. There was a known matrix, right? PBK. Somehow that is we were able to get rid of the condition by approaching with the congruence transformation, right? Ultimately that is we got BKY, something like that. Then here, that is in the case of ARI, here also that is we applied another trick of non-stick shoe complement lemma, then we convert the nonlinear matrix inequality to linear matrix inequality. So, but still these kind of cases are relatively easy. There are many other cases that is which are really difficult for us to convert into the element. Okay, and also this is not always guaranteed that is all nonlinear matrix inequalities can be converted into linear. As you know, that is the choice of nonlinearity is infinite. So that's why there can be like different very critical type of nonlinear matrix inequalities which is not possible to convert into element. Those things are, first of all, you will find if it is a non-convex optimization, or even that is even if you somehow are able to design it as a convex optimization problem, but still the constraints are so complex type that they are not coming as the linear matrix inequality constraints. So those are kind of like the different things, different in the sense for which really we are handicapped. We means then the applying the LMI techniques is really very difficult. But we will handle different types of examples. Like at this moment, as we are just going to learn the bounded real lemma, especially for finding the H infinity norm of a system, not by hand calculation through an LMI. That is like one of the pillar of robust control, which is applied everywhere in robust control, especially in H infinity controller synthesis. When we will learn the H infinity controller synthesis, whole like the derivation I will like take up on the board. There you will find that is many big terms will come together, and then that is how we handle those kind of things. Okay, so gradually actually we are learning one after another. What I wanted to say, suppose you have inequality where you have two unknown terms. Let's say that is the first case where you have that is P and K. Somewhat that is if one is kept constant, then it will become an element. Right? Then you have like two unknowns, P and K. Suppose if you keep K constant, or in a similar kind of situation where you have two unknowns, you are keeping one of them as constant and the other one is the variable as it was. Then it would be linear. Such kind of matrix inequalities are called BMI, bilinear matrix inequalities. Now bilinear is still not linear. We cannot directly apply the LMI technique, but bilinear matrix inequalities also appear in many places of control theory. There are many techniques by which we can solve BMIs, but of course they are not as elegant as LMIs. Mostly there some form of iteration is there. Like if somebody asks you that is okay, if you have a bilinear matrix inequality, what is the easiest choice you can think about? What you will do? Then keeping one variable constant, that is you will try to find out the other one. Then suppose for that first choice of the first variable, if the other thing gets true, then it is fine. But if it is not, then you will have to keep on changing the choice of the first variables. That from where the concept of iteration comes into the play. Are you getting? একবার বোধহয় তোমাকে পাঠিয়েছিলাম, ঠিক আছে? তো না হলে তুমি একটু খুঁজে দেখো, না হলে আমি এখন ক্লাসে আছি তো আমার আর 8 ঘন্টা পরে আমি না কোনো ব্যাপার নেই, আমি 8 ঘন্টা পরে ডেস্কে গিয়ে তোমাকে সবকটা পাঠিয়ে দিচ্ছি। ঠিক আছে, ঠিক আছে। So what I was explaining, that is suppose you have two variables, that is one is like P, another one is K. Now you know that is there are some, suppose there is a finite choice of K, and then for each one of them, if you run the LMI, that means the other part, then it is kind of a for loop. That is suppose for first choice of K, you are running the LMI. If that is true, everything is fine. Then suppose for the second choice of K, for K2 you are running the same LMI. For K3 you are running K4, K5 up to suppose K100. then in the simplest procedure, that is an iterative technique which can solve a BMI. Of course, it will not happen if you have 3 variables, because then it would be a nested loop. And if it is a nested loop, then the time complexity and the space complexity will both exponentially rise. So that's why that is for the BMI techniques, although there are other efficient techniques, but the easiest one is that you keep one of them as constant and run the other part. And of course, that is, there would be many choices which won't satisfy the other part. So you have to keep on changing the choice of the first variable. So that is the easiest process of solving a bilinear matrix inequality. Okay. Let's start with the bounded real lemma. Do you have any doubt so far, whatever we have learned? Can any of you tell me that what is a bounded real system? Focus on the name itself, bounded real.
For a bounded input, we are having some bounded output.
Not Vivo, bounded input, not even related to state, it is related to the gain.
So the maximum gain is finite.
If you have a system that is whose gain is always finite means starting from 0 frequency until infinite frequency, whatever may be the frequency, always you will find finite gain. That kind of system is called bounded real system or finite gain system. In other sense, those kind of, like the transfer function of those kind of systems belong to R8 infinity. Okay? So these are different names, bounded real or finite gain systems. And you can answer, sir, that why these different names come, because there are some other theories which relate to this. And if you say finite gain system, then not only they are linear time invariant, for a nonlinear system also we can define finite gain property. That is also a point you can note. What I said, that is, it is not that bounded real system or finite gain systems defined only for LTI systems. They can be defined for for nonlinear systems as well. Immediately you can argue that is, sir, H infinity norm, that is, or the way we have defined, it is for only linear time invariant system, because that is completely dependent upon the frequency domain response, the transfer function, based on which that is we found the gain and the maximum of all the possible gain, that is H infinity norm. And if it is defined, or if it has to be defined for nonlinear system, then how would you relate? For that, what will be the answer? When we define the H infinity norm, of course, frequency domain representation is more convenient for us, but we learn the time domain representation as well, right? That is through the operator norm. So, if you have to find out, or if you have to define the gain of a system in time domain, then we take the L2 norm. And that is if I ask you what is a finite gain system, what would you answer? If the L2 norm, or if the L2 gain of a system is exactly is finite. How do you represent? I will write it. Let me read the code. All these things are required, may not be for this course, but after that, when you will go through the book or you will read papers for your project, then all these kind of nomenclature and the concepts, expressions you have to encounter. So that's why I am giving you as much as information possible, because when I was a student, I faced all these difficulties. When I started reading from books and the papers, initially I couldn't understand any of the things. So then by searching from here and there, it took a long time for me to understand all these keywords and the basic definition. So that's why that is in my class I always try to give you as much as information, even which is beyond the syllabus. Can you relate the first part with the definition of H infinity norm? For any transfer function or transfer function matrix, if you can represent in this factor, that is the Gj omega star into Gj omega, it is lesser than equals to some gain into identity matrix, that is the signature of a bounded real system. That means whenever you multiply a matrix transpose by the same matrix, then what will happen? That is, from that you will be getting the square of the eigenvalues, right, of the matrix, and then which is directly related to the singular values through which you will be getting the H infinity norm. We will do it based on that only. We will derive the bounded real lemma. And this is for LTI. If it is for non-linear, then we try to frame it in the time domain. Okay, so here what does it say? That is the L2 gain of the output that is lesser than equals to some gain into the L2 norm of the input plus a constant term. Okay, this is not that significant. Actually, that is called the zero input bias, because not all systems will give you zero gain for zero input. Because suppose a system has some initial condition, so even if your U is 0, it can give you some gain, right? So that factor is your B. Now this is gamma. This is called the finite gain, and if this inequality is with respect to the L2 norm, it would be called L2 finite gain. If it is with respect to L1 norm or any other LP norm, then similarly it would be called LP finite gain. So for a system, if you find, that is, if you can represent a system into this fashion, and then if you get this a finite gamma, then you will say that that kind of system or that system is a finite gain stable system. In LTI cases, that is nothing but your bounded real system, or whose transfer function will belong to RH infinity. Okay. For non-linear, as we don't have frequency domain representation, of course you will have to go by the input-output approach, and this is the standard way how we express finite gain stability. So all this kind of system which can be represented in this fashion with the finite gamma, they are called finite gain stable systems. Okay. There is also one stability theorem. Suppose you have a negative feedback interconnection of two finite gain stable systems, they are non-linear, and under which condition that interconnection will remain stable. So then there is a theorem is there, if the product of the L2 gains of both the system, like suppose what I wanted to mean, this is suppose one system G1, here you have another system G2, and here you have a negative feedback interconnection. Okay, this gain is gamma 1, this gain is gamma 2, both of them suppose L2 finite gain, then under which condition this interconnection will be finite gain stable. See, if it is a non-linear, then, and in this case I am not saying asymptotically stable, I am following the input-output approach. That's why I say both of them are finite gain stable system. Then what is the condition under which their interconnection will remain finite gain stable? I never said the interconnection will remain asymptotically stable. Okay, so for that condition is, that is gamma 1 into gamma 2 must be less than 1. That is the finite gain stability condition for interconnected system. This is also called non-linear version of the small gain theorem. We will learn small gain theorem, that is one of the pillar result for robust control. nonlinear version. Now suppose what would happen, that is what will be the specialized form if they are LTI. Then of course that is that we can define their transfer function matrix G1 of S and G2 of S. Then in the LTI form they will belong to the space of RH infinity. Then what is the finite gain theorem? Can anybody tell me, that is if for the nonlinear this is the condition gamma 1 gamma 2 less than 1, then what will be the linear version in terms of H infinity norm? Linear version means the finite gain will have its H infinity norm counterpart. Then what would be the analogous or the corresponding condition for linear? That is H infinity norm of G1 into G2 less than 1. For the LTI case, the interconnection would remain robustly stable This is called Small-Gain theorem. We will need this one and come to this later. So this is about interconnected system, right? Because ultimately when we will move on to controller design, that means we will have to handle the interconnected system. There is a plan, then there is some uncertainty, disturbances as well, and in their presence we have to design the controller. So eventually we have to deal with the closed loop system. So that's why we need to know the results which apply to an interconnection, not only to a single system, right? What we can write by definition? We need this prefix, otherwise we cannot write the next part. writing this one, we need to have the A Hurwitz condition. Because otherwise, who will guarantee that this exists or not? Gj omega equals to C into j omega I minus a whole inverse, like the expression for Gs. Then instead of g omega star, what should I write? It will start with B transpose, right? B transpose and then minus j omega I is going to have complex conjugate transpose. So minus j omega I. Instead of A star, I am writing A transpose because it is a real matrix inverse C transpose plus D transpose. This whole thing into exactly the same means the non-transpose version C into j omega I minus A whole inverse into B plus D. Whole thing is less than gamma square I for all omega. That means here, what is the form I am using? It is Gs equals to C into Si minus A inverse into D plus D. If that is the situation, then immediately you can write Gj omega equals to C into j omega I minus A whole inverse into D plus D. And if you take the complex conjugate transpose, then exactly this thing will come, right? Now you take out the product, right? What will be the terms? B transpose minus J omega I. Please don't forget to write that A her is another thing. Okay, I'm writing only the mathematical part. Minus A transpose whole inverse into C transpose into C J omega I minus A whole inverse into B. Fine. So that is the first term. The second one is going to be B transpose minus J omega I minus A transpose whole inverse into C transpose. We are going to have a similar term which will be D transpose C, right? D transpose C, where it will be J omega I minus A whole inverse into B. Yes, we will have D transpose B lesser than gamma square I for all omega. Isn't it? After this, can we arrange it in a nice form? That is, a vector in between a matrix and another vector. I wanted to make. Tell me what will be the second term. Should it be I?
Same. One should be Z.
Why B? Already you have B transpose is here, and here you are getting B.
0. So,
0. No. If you have 0, then ultimately how would you be getting 4 terms back? Suppose simply this is an unknown matrix. Suppose this is X transpose and this is X. You find out this. You complete this product and then you tell me. Arun, should it be I? If it is I, you cannot have minus I. That is, you are saying either I or minus I. That I don't know. That is, you please say. बताइए क्या आ रहा है? Because here you have T transpose T and that's a whole term. Are you thinking that it should be minus because we don't have any minus term over there, right? Only the minus is here and that itself the term is appearing here, minus j omega I minus A transpose. All of you please check and confirm me whether this is I. Girvan, what are you getting? I. Confident it would be I, Atrevi? Now, if we reach up to this much, can you tell me that is here, that is what are the main problems? Ultimately, we want to find an LMI condition. So, in that sense, here, what are the difficulties we still have? What is the main difficulty? It is frequency dependent, right? Because here, that is, we still have j omega I minus A. So that is the main difficult part. That is, here it is a frequency dependent inequality. Do we have some technique which can convert a frequency domain matrix inequality into a time domain matrix inequality? No, here it is not in terms of like the signals. Here you see input output we don't have. Here all the matrices. How would you apply inverse Laplace? That is the problem. If it is input output representation where you have u of j omega, y of j omega, then you can apply the inverse Laplace. But here directly you cannot. Everything is with respect to the system matrices, frequency domain representation, but you don't have any input output signal. There is a technique called KYP lemma, which transforms a frequency domain matrix inequality into time domain. That we are going to apply. So let me first write down that is the main trick, KYP lemma. Its defined version came in around 1996 by one Swedish professor, Anders Ranzer. He is a professor of KTH, Sweden. This is Kivite dilemma. This is one of the most useful techniques for such kind of cases where you are starting in the frequency domain and then you have to get rid of the frequency domain condition. Okay. So now that is, can you see that is this form is exactly in this format. So this whole matrix is what? That is your M. And basically that is this gamma square I that you can limit here. That is, can't I write this one is same as d transpose d minus gamma square I and then it will be 0. I can write that, right? Have you written all this part? May I erase? right? And I'm starting from here, right? That is after this step. A's are this, and there exists a real symmetric matrix. P equals to P transpose. At this moment, I cannot write whether it is positive semi-definite or positive definite because that definiteness condition is not there in the equivalent lemma. Such that PA plus A transpose P, PP, B transpose P, 0 plus, I have to write the M. What is my M matrix? C transpose P. Then C transpose D, D transpose D, and D transpose C. And here you have D transpose D minus gamma square I. This whole thing less than 0, isn't it? Are you understanding? This gamma square I that I am bringing here. So this simply, that is, I can arrange a little bit. This is also equivalent, right? Now here we have almost reached our result. The only problem is this gamma square, right? Initially we started with gamma square, gamma square. So here you see that gamma is the variable, right? Gamma is the variable and the center P is variable. So we cannot allow any square of the variable, right? So either you have to substitute this gamma square by a new variable sigma, or else that is you simply you divide both sides by gamma. That can also be done. Okay. That is then what we can do. That is, if and only if, suppose I am dividing both by gamma, then all these variables will have a gamma term. So what we can do, that is, suppose P by gamma A plus A transpose P by gamma, and then 1 by gamma C transpose C. Here also you are going to have B transpose P by gamma plus D transpose C by gamma. Here also P by gamma into B plus C transpose D by gamma. Here also it is D transpose D by gamma. And then here it is gamma I. Right? In fact, from this step also, that is like you could have done. Like if you divide both the side, the right hand side is 0 and left hand side you have all the terms. As if that is you are dividing all of them by gamma. and then ultimately what will happen, that is suppose this wherever you are getting this term p by gamma, then you, since gamma is greater than 0, p is positively definite, so you denote this one by a different variable, suppose y colon equals to p by gamma. So this is your new variable, of course, like it will be symmetric positive definite, and then wherever you are getting that is only, that is 1 by gamma, you consider that 1 by gamma to be a different variable, that is like your sigma equals to 1 by gamma. So ultimately that is you will find, and this one, that is again we can bring it here, or anyway this can also be solved. So finally, what is that LMI? That is like minimize this gamma such that it satisfies. Because ultimately here what will happen, that is when you will run the LMI, we have to find out that gamma, that is which is a minimized value, right? So when we are defining, if you see the process, like the way we have started, the H infinity norm of that G of S, that is less than gamma, right? We didn't write that it is equal to, because if it is equal to, we cannot directly frame it into an LMI framework. So what we are doing, that is we are like finding the minimum or the infimum value of gamma, that is which is more or less equal to or close to the H infinity norm of GS, okay? So ultimately when you have a LMI, then this gamma, you have to find out the minimum or the infimum value of the gamma so that this LMI holds. Then ultimately it's not only a feasibility problem. If you have to find out the H infinity norm through this LMI, you have to write a minimum gamma so that this and that P equals to P transpose greater than 0, or Y equals to Y transpose greater than 0. Okay, so it has one more like simplified version. Okay, we will do that next day. You can also try. That is what I wanted to mean. Now here you have a 2 cross 2 block matrix structure. It can be translated into a 3 by 3 structure as well. That would be your like further convenient. Okay, at this moment it is a 2 by 2 block matrix structure. By applying should complement lemma, you can transform it into a 3 by 3 form as well. So ultimately what did I mean? That is here what is your bounded real lemma, that is if you have to apply it for finding the H infinity norm, so it is minimum, that is minimize gamma such that this whole entire LMI condition, that is after just bringing gamma this side, ultimately we have to express it like this, and P equals to P transpose or Y, whatever you write. Okay, so in this way you write that minimize gamma subjected to this LMI, but what is the underlying condition? P is a symmetric matrix and positive definite. If you transform it or if you convert it into Y, then instead of P you have to write Y equals to Y transpose positive definite. Okay. Don't worry, that is like today you are already exhausted, so that's why I didn't do the final simplification. Next day we will start from the last part again. Okay? Okay, guys, thank you. कोनिका एकदम इम्पेशेंट हो गई। मोइना तो बहुत पहले ही इम्पेशेंट हो गया था।
सर मेरे को ज़्यादा था, मैं दूसरे देता था।